In this episode, we're going to focus on one of the most underappreciated ideas in AI security: integrity. When beginners think about protecting data, they often think first about secrecy, like preventing a leak, but integrity is about preventing unwanted change and ensuring that what you rely on is still true. For AI systems, integrity is especially important because models learn from data, and if the data is wrong, manipulated, or inconsistent, the model can become unreliable in ways that are hard to detect. You can have perfect access control and still end up with a model that makes harmful decisions if the training data was quietly corrupted or if labeling practices drifted over time. Integrity also matters for defensibility, because when a system's outcomes are questioned, the organization must be able to show that the data and process were controlled and that changes were tracked. The AI Security Manager, AAISM, mindset is to treat integrity as a continuous discipline, not a one-time check at launch. By the end, you should understand what data integrity means in AI contexts, where integrity commonly fails, and how high-level integrity practices keep models trustworthy over time. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A clear beginner definition of data integrity is that data remains accurate, complete, consistent, and unaltered except through authorized, controlled changes. Accuracy means the data values reflect reality as intended. Completeness means important records are not missing in ways that distort patterns, and consistency means the same concept is represented the same way across sources and time. The unaltered part means that if data changes, you can explain why, who changed it, and what approval or process governed that change. In AI, integrity is not only about raw values, it is also about labels, metadata, and transformations, because those elements guide what the model learns. Beginners sometimes assume integrity issues are obvious, like a file being replaced, but many integrity failures are subtle, like small shifts in labeling rules that create inconsistent categories. Another subtle issue is that integrity can be lost through well-intentioned cleaning that removes too much information or changes distributions without documentation. Integrity also applies to the separation of training and test data, because mixing them undermines honest evaluation. When you understand integrity as controlled correctness over time, it becomes easier to see why it is central to trustworthy AI outcomes. Integrity preservation begins with provenance, because you cannot trust data if you do not know where it came from and what it represents. Provenance means recording sources, collection methods, timestamps, permissions, and any constraints on use. In AI programs, provenance also includes understanding whether data was collected for the current purpose or repurposed, because repurposing can introduce hidden bias or legal risk. Beginners should recognize that provenance is not only a compliance concern, it is an integrity concern, because unknown origin data often contains unknown quality issues. If a dataset includes records from multiple systems with different definitions, the model may learn inconsistent signals, producing unreliable behavior. Provenance also supports investigation, because if a model begins behaving strangely, you can trace which data sources might be responsible. Another important point is that provenance should include transformation history, because a dataset is rarely used in raw form. When you treat provenance as a first-class attribute, you create a foundation for integrity checks that are grounded in reality rather than guesswork. Provenance is the story of the data, and integrity depends on a story you can defend. Once provenance is understood, integrity preservation requires control over who can change data and how changes are managed, because uncontrolled edits are the fastest path to invisible corruption. Access control helps by limiting write permissions, but integrity also requires process, such as requiring approvals for meaningful dataset changes and recording change rationale. Beginners often assume that if a trusted internal team member makes a change, it is safe, but internal mistakes can be just as damaging as malicious tampering. A mature approach separates roles, so the people who approve data changes are not always the same people who execute them, which reduces the chance of errors slipping through unnoticed. It also requires that dataset updates are performed through controlled workflows rather than ad hoc edits, because controlled workflows produce consistent logs and allow review. Another important concept is that integrity requires the ability to revert or compare versions, because if an update introduces problems, you need a way back. Version discipline is therefore a practical integrity control, not a technical luxury. When changes are controlled and traceable, the organization can maintain trust and respond confidently when outcomes are questioned. Data quality checks are another critical integrity practice, and they are often where beginners gain the most practical understanding of integrity. Quality checks include validating ranges, detecting missing values, spotting duplicates, checking formats, and identifying anomalies that suggest corruption. In AI datasets, quality checks also include checking distribution, meaning whether the proportion of categories or values shifts unexpectedly, because unexpected shifts can signal either a data pipeline issue or a change in the environment. Beginners should understand that a model can be sensitive to distribution shifts, because if training data has one pattern and real-world inputs have another, reliability suffers. Quality checks should also address label quality, because mislabeled examples teach wrong patterns, and small labeling errors can create large behavioral changes. Another useful practice is sampling, meaning reviewing a small subset of data manually or through structured review to confirm that automated checks are not missing context. Quality checks should be repeatable and documented, because the ability to show what checks were performed is part of defensibility. When quality checks are a routine, integrity problems become detectable signals rather than hidden time bombs. Labeling integrity deserves special attention because labels are essentially the answers the model is trained to learn, and poor labels create unreliable learning. Labeling can be corrupted through misunderstanding, inconsistent definitions, rushed work, or even intentional manipulation. Beginners might think labeling is straightforward, but many real labels involve judgment, such as whether content is abusive, whether a transaction is fraudulent, or whether an outcome is acceptable. If labelers interpret rules differently, the dataset becomes inconsistent, and the model learns contradictions that show up as unpredictable outputs. A mature integrity approach defines labeling guidelines clearly, trains labelers, and uses review and sampling to detect inconsistency. It also tracks who labeled what and when, because traceability helps identify the source of errors. Another important practice is measuring inter-rater agreement, meaning whether different labelers assign the same label to the same type of example, because low agreement signals integrity risk in labels. While beginners do not need to calculate metrics, they should understand the concept that labeling consistency is part of integrity. When label integrity is protected, model reliability improves and governance becomes more defensible. Transformation integrity is another area where data can quietly change meaning, especially in AI workflows where data is cleaned and reshaped. Transformations include removing fields, normalizing formats, encoding categories, and filtering records, and each transformation can change the patterns the model learns. Beginners often assume transformations are always improvements, but transformations can introduce bias by removing information unevenly or by filtering out minority patterns that are important for fairness. Transformations can also break traceability if the transformed dataset is disconnected from the original source, making it hard to explain what happened. Integrity preservation, therefore, includes documenting transformations, maintaining links between raw and transformed datasets, and controlling who can modify transformation pipelines. It also includes validating that transformations produce expected results, such as confirming record counts and distribution changes are understood and justified. Another common integrity problem is that different teams apply different transformations to similar data, producing inconsistent results across models. A mature program reduces this inconsistency by defining shared transformation standards and by reviewing changes to transformation logic. When transformation integrity is managed, the organization can trust that the dataset still represents what it claims to represent. Training and test data separation is a special integrity requirement because it protects the honesty of evaluation, which is essential for trustworthy decisions. If test data leaks into training, the model may appear to perform well during evaluation while actually failing in real conditions. Beginners sometimes think this is a technical detail, but it is a governance issue because it affects whether deployment decisions are defensible. Separation requires both process and controls, such as distinct storage locations, restricted access, and clear rules that prevent reuse of test data in training. It also requires documentation so teams can prove which data was used for training and which data was used for testing. Another important concept is that test data itself must have integrity, because if test labels are wrong or test examples are outdated, evaluation results become misleading. In AI governance, maintaining separation supports confidence and reduces the risk of deploying systems that are unsafe or unreliable. When separation is maintained, the organization can trust the evidence it collects about model behavior. That trust is foundational for both security and compliance. Integrity also depends on protecting the data pipeline, meaning the processes that move data from sources into storage, transformation, and training environments. Pipelines can fail through bugs, misconfigurations, unauthorized changes, or dependency changes, and pipeline failures can introduce silent corruption. Beginners should understand that pipeline integrity is about ensuring the pipeline does what it is supposed to do and does not do what it is not supposed to do. This includes controlling pipeline changes through change control, monitoring pipeline outputs for anomalies, and validating that pipeline outputs match expectations over time. Another important practice is implementing checkpoints where data is validated before it is promoted to the next stage, such as before being used for training. Pipeline integrity also includes dependency oversight, because a change in an upstream system can change data formats or values, causing downstream distortions. In AI systems, pipeline issues can appear as model drift or performance changes, and without pipeline integrity, teams may blame the model rather than the data. A mature program therefore treats pipeline integrity as part of model reliability. When pipelines are controlled and monitored, integrity failures are caught earlier and corrected with less harm. Third-party data and vendor involvement introduce additional integrity challenges because the organization may not control the full chain of custody. If training data is acquired from external sources, the organization must validate quality and trustworthiness, and it must document provenance and permissions. If a vendor model is used, integrity includes understanding how updates occur and ensuring that changes are tested and approved before deployment. Beginners should recognize that vendor updates can change model behavior, which can be perceived as integrity drift even if no dataset was altered internally. For third-party data, integrity risk includes poisoning, incomplete documentation, and hidden bias, because external datasets may not match the organization's context. A mature approach includes due diligence, sampling and quality checks, contractual expectations, and monitoring for changes in external sources. It also includes updating inventory and classification when external dependencies change, because compliance scope and risk posture may shift. This is another reason integrity is connected to governance routines, because governance is what enforces consistent oversight of third parties. When third-party integrity is managed, the organization reduces the risk of adopting unreliable foundations. Integrity preservation must also include operational monitoring and revalidation, because integrity can degrade over time even without malicious activity. Data sources can change, business processes can evolve, and user behavior can shift, leading to distribution changes that make old training data less representative. Monitoring can detect these changes by tracking data quality signals, distribution patterns, and model performance indicators that suggest drift. Beginners should understand that drift is not always a failure, but it is always a signal that requires attention, because it can lead to harmful outcomes if ignored. Revalidation means rerunning evaluation checks after meaningful changes, such as new data sources, new transformation logic, or model updates, to confirm that reliability and safety remain acceptable. Revalidation also includes reviewing whether fairness and privacy risks have changed, because integrity issues can amplify those risks. This operational loop connects integrity to routine governance checks, because governance defines when revalidation is required and who approves changes. When monitoring and revalidation are disciplined, integrity becomes a managed property rather than a fragile assumption. This is how models remain trustworthy in the real world. As we wrap up, preserving data integrity is about ensuring that the data feeding an AI system remains accurate, consistent, and controlled so the model stays reliable and the organization can defend its decisions. Integrity begins with provenance and traceability, so you know what data is and where it came from. And it continues through controlled change management that limits who can modify data and documents why changes occur. Data quality checks and labeling consistency protect against subtle corruption that can cause unpredictable behavior, while transformation documentation and validation prevent meaning from being lost silently during preparation. Training and test separation protects the honesty of evaluation, and pipeline integrity ensures that data movement and processing do not introduce hidden errors. Third-party involvement adds chain of custody challenges that require due diligence and monitoring. And operational monitoring and revalidation maintain integrity over time as environments shift. For a new learner, the central takeaway is that integrity is not a background detail. It is the reason you can trust model behavior and the reason you can defend outcomes when they are questioned. When integrity is preserved through disciplined routines and evidence, AI systems become safer, more reliable, and more sustainable for the business.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.